so this is a bit different from the theme of this conference, but it has some commonness that involves homogeneous spaces. So the aim is, I have this complex Lie groups, semi-simple Lie groups like consider complex semi-simple Lie groups, and G is the Lie G, and I consider X to be a nilpotent elements. G, I consider the orbit under the adjoint axiom, and I'd like to know what is the dimension of this vector space when considered as a real manifold, and we will give a complete description of this, and this is a joint work with Indranil Biswas, Bombay. So first, I will try to motivate why I'm looking at this. So there are 2 points which sort of led us to this, asking this question, that what is the description of second cohomology of nilpotent orbits. The first thing is comes from the exactness criteria of Krylov form on orbits, the coadjoint orbits in, that means the orbits in G dual, and secondly,
excuse me, what does OXR mean?
OXR means, I have this OX means, at GX, G in G. So this is my manifold, and this is the second de Rham cohomology of this. Yeah. So and secondly, the first, I'll explain why these two topics. So we can, so there are certain very special nilpotent orbits called regular nilpotent orbits. I'm going to define what they are. Consider G. Then one can show, I'll show this, that H2 of OX, regular nilpotent orbits, so X, so I consider a regular nilpotent element. I'm going to define what they are. So if X is regular in G, then H2OX. So yeah, so I'm going to define what there. I mean, just some. I'm going to define what. So these two things led us to ask what is the general description. Like from the exactness criteria that I'm going to show, it shows that if I take the Costa-Krylov form on a nilpotent orbit, then that's going to be exact. So the more generally, if I take any orbit, take any x in G and take the corresponding adjoint orbit, then the Costa-Krylov form is exact if and only the eigenvalues of add x are all here. That's what I will do. But in particular, if I take a nilpotent orbit, then this says the eigenvalues are all 0 in particular, so the Costa-Krylov form is exact, 2 form is exact. So one may ask, what is the general description of the second cohomology group for nilpotent orbits? And this is what we are going to answer at the end, but let us prove this exactness criteria and this second statement. So first define what a Costa-Krylov form is. So it's a very natural 2 form on orbits which makes orbits a simplex manifold. So first is defined on the orbits on of G on G2. So definition. Yeah. Okay, so I consider I have this action of G F by composing F compose G inverse. Then consider OF to be GF. Now define a 2 form on the, so define WF, a 2 form on the tangent space at F of OF cross R by by to the F of xy, where phi f is a map from G to where given by phi f. Orbit. Okay. So this form is very naturally arising, and this form is has this property that properties. So I can do it for every point in the orbit, like in a similar way. So this gives a left invariant. So W and this points G invariant for F. This is closed. Non-degenerate. So this is a definition of Costa-Krylov form. So so this makes the orbit, the coadjoint orbits a simplex manifold. So in particular, one can prove that the wide-joint orbits are of event dimension. This is very nice phenomena. But when I have this semi-simple Lie group, I have this G equivalent map from G to G star using the killing form. So that makes every orbit, the adjoint orbit is also a symplectic manifold. So this is true for any Lie group. I mean, you can give this form on any Lie group. But if G happens to be semi-simple, via the filling form. So every orbit in G is also a symplectic manifold. So every orbit is also of even dimension. This is not easy to prove that every orbit in G is even dimension, but one proves using the fact that these are symplectic manifolds. Okay, so this Boston Krylov form arises in a very natural way when you study adjoint orbits and geometry, symplectic geometry, and so on. So we are going to prove a theorem which says symplectic forms are of course closed, but it is not always exact. We are going to give a criteria when it's exact. So let me state the theorem. Finite center, assume that any maximal, any A maximal, maximal compact group semi-simple group of let x be in G, then if G is semi-simple, then you can transport the Boston Krylov form from G12 to G. As I said, it is a G equivalent map. So via the killing form, then exact. So one immediate corollary is if x is nilpotent or at this is a very special type KK form. Boston Krylov form is a very special type of two form in OX. This is exact on nilpotent orbits using this theorem. but so let me come back to the proof of this one if I have time later on, but hopefully I have some time. But first, let us give the proof of the other motivation that's a very short and easy proof. So let me do that. So the second, I want to call it lemma. So here I have a very canonical two form which is exact on nilpotent orbits. But on the other hand, if I take x to be, so let x be a regular nilpotent G. Here G is complex sensible. G is sensible. Then so let me explain what regular means. So definition. So regular nilpotent elements are the nilpotent elements for which the centralizer of the nilpotent elements at the least dimension or the orbit, the dimension of the orbit as the greatest dimension. So in general, if I take the variety of nilpotent elements, it has the dimension is the dimension of the Lie algebra minus the rank of the maximal torus. So the orbit of a regular nilpotent element is exactly has the same dimension, that is dimension of the Lie algebra minus the rank. So for example, so definition is as follows. So x, so I consider n be the set of variety of nilpotent elements G. Then x is called regular if dimension of x G is greater. Okay, so example of regular, if I take the simple case of SLNC, then just so if G is SLNC, then I consider diagonal. So just above diagonal, consider take all ones. Okay. If I take anything non-zero in all the entries just above the diagonal, then this is an example of it. Example of. You take x is this. And if you take the, for example, in simplest case of SL2, SL2C, this is an example of regular. So if I take such orbits, then we have this. Now why is this true? Because we have a, so let us give a proof of this lemma, which is short. So proof is as follows. So first thing to note is, so OX is of course, OX is same as, where this is the centralizer of X. So, but we have a clear description of the centralizer of X when X is regular, which is, so when X is, So okay, let me set up some notation. So let U be XX. So this is a unipotent element. So let G be the complex group for which N of G is this. So unipotent element in G. And I consider B a Borel subgroup containing U, and let U be the unipotent radical of E. Also let T be the torus, T be a max torus B. So we have this B, this U, but this, let us discuss the centralizer. So the centralizer has this description that it is center times the centralizer of X unipotent. If I either you can take X or U, it doesn't matter. Okay? So U is the unipotent radical of the Borel containing U. So this has this description. Okay, now I have this Iwasawa decomposition of this G, which is I take A to be R split. I take all positive eigenvalues of elements in P part connected. Split part of T. Then I am K be a maximum compact. G, then note that we have this K cross A U, G, I have this X, Y, X, Y, secure. So now using this description, so these two things in mind, one can say that G by ZGX is diffeomorphic of K by ZG cross AU by ZUX. Okay. So, but this is a Euclidean space because after all I am modding out by this A is a Euclidean space and U is a Euclidean, U is a unipotent group. I am modding out by a unipotent subgroup. So this is just some RD. Okay. So the topology of this is, I mean, the homotopy type is controlled by this. So H2 is same as H2 of K by G. Okay, and K is a maximal compact, and my group is a complex semi-simple group. So K is a maximal compact in that complex semi-simple group. So this is a real semi-simple group, and so by Whitehead's theorem, this is by Whitehead law. Okay, so this proves that since K is this proves that H2 is of a regular unipotent orbit. The theorem homology is Okay, so now let us get into the other topic. Probably at the end, I'm just going to describe the results. So, to prove the exactness of and also compute the second cohomology of equivalent orbits, I need a suitable description of the second cohomology group of a general homogeneous space. So let us write this as a proposition. So G is a real G group. H is a closed subgroup. Probably small transmission. Yeah, again I need the maximal compact. Assume H has finitely many connected components. And also assume that maximal compact, any maximal compact G is semicircular. Then H2 of G mod H is, there is a natural isomorphism between H2 of, okay, so set up another notation. K, maximal compact H, then H2 of G mod H. There is a natural isomorphism between these two vector spaces. I consider the center of the Lie algebra of the compact, maximal compact in H. I take the dual of that and consider the, so K acts on this space and K not acts trivially on this space. So this means I have action of K by K naught on this object and I consider the fixed points. Fixed point on this. So these two are isomorphic. Okay, so so I am not going to prove this, but a corollary from the proof is as follows, which will tell us, corollary while proving this statement tells us that, so before writing the corollary, let me set up some little bit of notation here. So I have, so let M be a max compact of G containing K. K is the maximal compact in the smaller one, H. Then I have this map M by K to G mod H. So the property of this is that G mod H is M by K, this space is going to be a deformation retract of G mod H. This is a result of Moscow. But he proved only for H connected, but even if H is as finitely many connected components, the same thing goes through. So if I have a form closed. So let's call this map P. In a closed form in G mod H, then phi star W is. So this is a this is going to bundle over this, and the fibers are retractable, so it's going to be a tract. And so this form is closed, implies this is closed, and this is a form phi star omega is a form on this, and by general theory one can get a M invariant form W2. W2 is M invariant. Since M is compact, you can get M invariant form on W2 on this, so that this is exact. But M invariant forms on M mod K is determined by what happens at the Lie algebra level at the identity, I mean of the so M invariant means M is acting transferable, so it just depends on what happens on the point. So M invariant form are in bijection with forms on M mod K, and I need to, since it is M invariant, so at the tangent space level it should be, at that level it should be at K invariant. So this K is acting on this quotient space by adjoint action. So I need forms which are invariant on this adjoint action. Okay? So this W is exact if and only WT is exact, and W2 is going to be d eta. Since I confused between WT on the whole space, so WT maybe WT corresponds to some W tilde. So W tilde is a form on this. So W tilde is going to be closed. So this is going to be d eta again by Whitehead's theorem for some eta, which is a one form on M. Now the proof of the previous statement says that this W, if you go through the proof, which unfortunately I am not going to say, this form W is exact. So the corollary is finally this. W is exact if and only eta, which is a linear function on M. M, I should say M mod A. M eta of okay. So this is a criteria for exactness in general space, and we are going to use this to determine the exactness criteria for a form on a general adjoint orbit. And here is the proof. Proof is okay. So I take X. X is generally, so recall that G is a real semi-simple Lie algebra. Then G has this complete Jordan decomposition that every element can be written as three commuting elements. One of them is as purely imaginary eigenvalue, that is the compact part, and one has the hyperbolic part of the real eigenvalues, and other one has the eigenvalue at 0. So take X to be in G, then X has this complete Jordan decomposition, xk plus xh, h plus x. K is compact. This is hyperbolic. And they all mutually commute. Now, the form that, so consider f of x, that constant form comes through is the b of xy. B is the b form. Now, this kk using that corollary is exact. Max compact. It's not fx but dfx. D is exactly the form that I'm interested in. Okay, so now this says, this is one only, b of x Okay, so now you see, now one needs to like a simple property of the clean form is if I have b x and okay, so x and x h is 0, or maybe for xs for any Samsung x t xk, t is in R, consider this group and consider, take the closure, this is going to be compact subgroup for xk x and choose a maximal compact, let k be a max compact containing, let's call this S. Then this condition is same as saying using this, this and this is equivalent to saying that B of xk, at least, yeah, B of xk is, which is same as saying this, so xk is 0 means the compact part is 0, that means all eigenvalues are real, so which is same as saying x this proves the exactness criteria. Now, this, as I said, the exactness criteria of KK form and second vanishing of regular inbound orbits leads us to asking a very natural question: that what is the description of second cohomology of all the inbound orbits? Okay, so here is theorem, but not state the full theorem, but it needs some notational setup. But let me draw an interesting corollary of the theorem. Okay. So the corollary is, so the theorem is we can give dimension of H2OXR for all nilpotent elements X in G for all complex sensors for G. So corollary is the following. Everybody writes a vanishing theorem at the end. So we have done that. If G is SP2N, G2, F4, E7, E8, then H2. That's 0. Okay, and for SLN, one can give a very nice description. So orbits, nilpotent orbits in SLN is in bijection with the partitions of the integer n. So SLN, then and D is a partition and X is important element corresponding to D, then dimension of H2OX is same as D minus 1, where is the number of distinct elements. So every nilpotent orbit corresponds to a partition, and if you take the number of elements in the partition to be modulus of D, then this is exactly D minus, which coincides with the regular case.